Welcome. Thank you for being here today. Good evening, and all the people that are connected with Zoom. We have the pleasure of having Professor Lida Cosmetic, distinguished visiting professor at UDD, and Professor Ernesto Silva is going to evening, and all the people that are connected with Zoom. Yeah, Professor Lida Cosmetic.
There are two Denises.
There's the ghost. There. So Professor Doctoradps is going to say a few words to welcome her.
It's still happening.
I know it's still happening.
I think you need to turn off the volume on.
Where's the guy?
There are two Denises.
There's the ghost. Doctoradps is going to say a few words to welcome her.
It's there, you have to silence. I think you need to turn off the volume on.
There are two Denises.
There's the ghost. Sigue. Doctoradps is going to say a few words to welcome her.
Todavía puede que haya dos micrófonos acá. Tienen que haber dos micrófonos acá.
Ay, no,
Todavía puede que haya dos micrófonos acá.
La transmisión se abre de UDTV.
Se cortó.
¿Les van a oír o no?
Está listo. El segundo objetivo, el primero.
Lilian?
You made fun of me.
She was all worried.
Just a few words and just a few words. It's really great for Universidad del Desarrollo to have you here again. We have at FIX and our doctorate program a very, I would say, very interesting approach in terms of having an interdisciplinary approach, where Professor Cosmedes has been a very relevant contributor over years. We don't have a lot of visiting professors that have the status of something that is funny because it's permanent visiting.
I like it.
Professor, but I think you were number one, right? So it's great to have you here again. We would like to have more kind of collaboration of this type for the future. And in terms of having you here, it's a great honor to know that you've been elected to the American Academy of Art and Science. Congratulations for that. We can imagine how proud you are and your colleagues for this achievement. We also feel proud because we feel you as part of our community. So I'm happy, Denise, that you are organizing this activity and the faculty members are here. And Professor Cosmedes' talk today is about evolutionary psychology and rationality, resolving the paradox of excellent performance by an irrational mind. So welcome again, and thank you very much.
Thank you.
Okay. So in How the Mind Works can be illuminated by comparing human cognition to standards of good design that are specified by a normative theory. But the question is, which normative standards count as good design for an evolved organism? The goal is to discover sophisticated computational systems in the mind, and that's always my goal. The question is, which normative standards should guide your research? And what counts as a rational inference? So research on the psychology of reasoning and decision-making began in the 1970s. And what people did was they compared human performance to normative standards of rationality that were favored by mathematicians, scientists, economists, and philosophers. And the assumption was that good design is the same, it means performance conforming to whatever principle of rationality you're interested in. And the question became, are humans rational? We'll see. So the research strategy that people were pursuing was they were comparing deductive reasoning and inductive reasoning to first order logic, to Bayes' rule, to various principles in probability and statistics. And they were asking, well, do we learn about the world by generating hypotheses and then testing them? Do we apply Karl Popper's standards where we put forth a hypothesis and look for violations of the hypothesis rather than just confirmation? And so decision-making was compared to Neyman-Pearson decision theory, that's signal detection theory, expected utility theory, rational choice theory, and moral judgment was compared to normative principles from ethics, asking, do people apply a single overarching normative principle when they're making judgments, like Jeremy Bentham's utilitarian maximize aggregate welfare or Kant's don't inflict harm. And so in this research tradition, what counts as an error? In this research tradition, reasoning errors were defined as having occurred whenever human judgment departs from what these normative theories of rationality dictate. So this is a famous quote from Daniel Kahneman and Amos Tversky. The presence of an error in judgment is demonstrated by comparing people's responses either with an established fact or with an accepted rule of arithmetic, logic, or statistics. So when cognitive performance was assessed by these normative standards, the rationality of human reasoning, judgment, and decision-making was found wanting. There were systematic errors in deductive reasoning and hypothesis testing, violations of probability theory, preference reversals that shouldn't be happening, excess altruism, and inconsistent use of moral principles where people would flip-flop between different kinds of judgments. So the question is, why these deviations from rationality? The most common explanation that was given by many people is that human cognition is riddled with heuristics, biases, and emotions that produce errors and fallacies. They may work a lot of the time, but they systematically produce all kinds of errors. And these heuristics, biases, and emotions, they preempt, interfere with, or bias deliberative reasoning. And people assume that deliberative reasoning is the kind of reasoning you're doing when you're learning math. They assume that deliberative reasoning is necessary for rational judgments, to apply rules of logic or to perform calculations. So psychology's focus on normative theories of rational inference that were used in science, math, economics, philosophy, and the research it inspired, and the theories proposed to explain the results, create a paradox. So on the one hand, people are saying human cognition is irrational, riddled with these error-prone biases and heuristics and emotions that cause performance to deviate from these great normative ideals. Yet evolved inference systems, humans and other animals, solve natural tasks far better than the most sophisticated existing AI systems, although Ricardo tells me that tomorrow that won't be true anymore. So babies with very limited perceptual input and no teaching, they segregate the world into objects. They know that when I go behind the screen, I continue to exist. The objects continue to exist when hidden. They know that two solid objects can't pass through one another. They induce the grammar of their native language. They infer beliefs, desires, and intentions of other people, what's called theory of mind. They do all of these things very quickly and very easily. So how is this possible? Even more puzzling is that it's trivial to equip an AI system with algorithms that implement statistical decision theories or inferences of first order logic and other formal methods of rational inference. And these systems can search these vast problem spaces in seconds, perform lightning calculations, analyze massive databases. So if these methods of rational inference are important for acquiring knowledge and producing intelligent, flexible responses, and our mind lacks them, then why do evolved organisms perform so well? Why do we perform better on virtually every natural inferential problem that has been carefully investigated? So what's the resolution to this paradox? From the perspective of evolutionary biology, the problem is not that our thinking is irrational. The problem is how psychologists have been defining rationality and testing for its presence. So I want to ask a more fundamental question. Why identify rationality with adherence to normative theories from logic, mathematics, economics, and philosophy? What normative theory justifies the choice of these particular normative theories? Is there a more general view of rationality for which these normative theories are a special case? So a more general view of rationality that is common in everyday life and in specialized fields like engineering, economics, evolutionary biology, vision science, evolutionary psychology, is that a process, choice, or behavior is considered rational when it's well designed for achieving a goal, and irrational when it's poorly designed for that function. So on this functional view, there's no goal-independent definition of what counts as rational. So are these things rational or irrational? So you're eating charcoal instead of fruit. Well, that's irrational if you're hungry and you want to be not hungry, but it's rational if you ingested a poison. It'll absorb the poison. Zigzagging from location A to location B instead of following a straight line path. Rational or irrational? It depends. It's irrational for saving time and energy, but it's rational if you're evading predators. This is what animals do when they're evading predators. Unpredictably, you want to be unpredictably zigzagging. Conversing out loud when you're alone. Irrational for communicating with another person, but rational if you're rehearsing a role. So the question is, are these methods of inference rational, the ones that we've been talking about, logic, probability theory, etc.? On the functional view of rationality, it depends on what they're for, on what they're being used for. These are specialized and historically recent tools that are well designed for achieving very specific goals that are evolutionarily recent. Producing scientific knowledge, understanding markets, and maybe guiding behavior in modern mass societies. There's novel problems in modern mass societies. The insane technological change that's happened since 1400 to the present. There's been vast increases in literacy, reliable data storage technologies, decreasing costs of communication and travel. That's changed the world beyond anything known by our hunter-gatherer ancestors. So theories, hypotheses, and data became much more widely shared, debated, vetted, stored, allowing the cultural accumulation of knowledge in ever larger populations. Markets arose in which millions of anonymous individuals cooperate in complex networks. And people from distant locations with different moral norms were brought into contact. So in these new conditions, a lot of the normative theories of rationality created by scientists, mathematicians, etc., they may be very well designed for producing scientific knowledge, for understanding market dynamics, for fostering cooperation in mass societies with global contact, maybe, we don't know yet. But the question is, what privileges methods developed for these modern goals as the metric against which human rationality is measured? I would argue nothing. So in an evolutionary perspective, rationality in an evolutionary perspective, achieving these modern goals played no causal role in selecting for the design of the mind. They're not the problems the mind should be well designed for solving. So to discover rational design in the mind, we need to take a functional view of rationality, an evolutionary functional view. So what I'm going to call the adaptationist research program provides a metanormative theory of rationality that's appropriate for evolved organisms, including their cognitive systems. So in this view, an evolved computational system has a rational design if its features are well tailored for solving an adaptive problem faced by the hunter-gatherers from whom we are descended, because of the following. Organisms are composed of many machines, that is, many systems that are organized to solve a problem. Hemoglobin is improbably well designed for delivering oxygen to tissues, lungs for gas exchange, retinal cells for transducing photons. Chance alone does not produce organic machines that are improbably well designed for solving problems like this. Natural selection does, though. Organic machines that were designed by natural selection are called adaptations in evolutionary biology. They exist because they solved problems that contributed to the organism's ability to produce offspring in past environments. Some of these organic machines evolved because they performed computations that regulate physiology and behavior. These are computational adaptations. And like other adaptations, they exist because they solved problems that contributed to an organism's ability to produce offspring in past environments. For example, detecting and evading predators, learning what's edible, managing foraging risk by sharing food with others, identifying objects by just using the reflectant properties of surfaces. An adaptation's function in biology refers to the adaptive problem that's selected for its design. And every adaptation can solve problems, can solve other problems that were not part of what's selected for its design by virtue of its causal properties. But these beneficial effects, like if I'm surfing, well, I can't surf. If I could surf, that would be a byproduct of me standing on two legs, walking with bipedally, et cetera. Those beneficial effects are not its evolutionary function. Because producing those effects played no role in the causal explanation for the organism's design features. Given enough time, natural selection produces adaptations that are well designed for solving ancestral adaptive problems. That is, their design is rational, that is well achieved in the sense that they're well designed for achieving a goal. So, computational adaptations that produce inferences, judgments, and choices should be well designed for solving ancestral adaptive problems that selected for their design. And analyzing these problems is a key to recognizing and then discovering sophisticated computational systems in the human mind. And it sheds new light, as I'm going to show you, on human reasoning and decision-making. I'm not good with this clicker. Okay. So in an adaptationist analysis, there's a 5-step program for discovering the design of the mind. Step 1 is just identify an enduring adaptive problem that our hunter-gatherer ancestors faced and ask, what's the goal of processing? For example, it might be cooperating for mutual benefit. It might be detecting changes in the state and location of animals that could be predators, they could be prey, etc. Step 2, do a careful task analysis of that adaptive problem. So to solve that adaptive problem, to achieve the goal of processing that you're hypothesizing, what design features would a computational system need to solve that adaptive problem well? And this is just as important, what information would have been available in ancestral environments for solving it? And lots of things are helpful for this. Results from evolutionary game theory, from agent-based models, from behavioral ecology, studies of existing hunter-gatherers, non-human primates, other animals, studies of ancestral environments that include not just from paleoanthropology and so forth, but from physics, geology, botany, zoology, etc. Step 3 is to use that task analysis to derive hypotheses about cognition, because a computational adaptation should deploy algorithms and representations that are well engineered for solving the problem that's selected for its design. So you ask, what properties might a system that evolved for this function have? Step 4, you test these hypotheses empirically. You do these things before you start. There should be a reason for your hypotheses, not that I was playing pinball and something jumped into my mind. This prior process is helpful. You test the hypotheses empirically using whatever methods are appropriate to your question. It might be laboratory experiments from social developmental cognitive psychology, it might be behavioral economics, it might be cross-cultural field tests, dissociations caused by brain damage, evidence from sociocultural anthropology. And that includes tests against alternative computational designs that have been proposed. Step 5, you want to evaluate the empirical evidence and ask, is there evidence for a computational system that's well designed for solving this adaptive problem? Is the proposed goal of processing achieved? And if so, are the cognitive processes responsible? Are they specialized for this function? I apologize, I'm having trouble. Or Do they seem better designed for an alternative adaptive function, one that you did not consider, that could produce the same performance? So these kinds of adaptationist analyses provide principled, non-arbitrary criteria for judging rationality. A careful task analysis of an adaptive problem serves as a normative theory of good design. Theories of adaptive functions specify the goal of processing and what would count as a good method for achieving it. From this point of view, the study of reasoning and choice ends up looking different. As I'll show you, a lot of fallacies disappear and well-designed reasoning appears when cognitive performance is evaluated against theories of adaptive function, which are normative theories of good design. So using several case studies, I'm going to illustrate some principles of adaptive design and show how research using each of them led to new discoveries and insights that people hadn't seen before, and how research ignoring this perspective led to some faulty conclusions. So case study number 1. To discover a well-designed reasoning mechanism, you need to present stimuli in an ecologically valid format. And the example I'm going to use here is Bayesian inference with natural frequencies. So here's a design principle. Computational adaptation should be what I'm going to call ecologically rational. That is, designed to operate well in the ancestral environments it selected for their design. So consider this completely ordinary, but it's a computationally spectacular experience. This grass looks green at sunset and at noon, both. That's called color constancy. And color constancy is maintained over the day despite vast changes in the spectrum of light that's reflected off of the grass. Color vision evolved for daily variations in illumination from our sun. And these are the spectrums of natural light at daylight and during daylight and sunset. And grass reflects more short and medium wavelengths at noon and more long wavelengths at sunset. But grass doesn't look red at sunset, despite the fact it's reflecting much more long wavelength red light. Because these color constancy mechanisms are ecologically rational, they're designed to operate well in the ancestral environments it's selected for their design. So if color constancy mechanisms are so well designed, then why do these cars look the same? Actually, one is red and one's black. That's a complete breakdown in color constancy. It's a failure of color constancy under sodium vapor lights in a parking lot. Sodium vapor lights literally cast an unearthly spectrum, a different spectrum than we have on Earth. But do we want to say that that failure in color constancy means color vision is flawed or error prone or biased? No, because there's no such thing as a mechanism that's going to operate well in all possible universes. Color vision evolved on Earth, and it maintains color constancy across typical variations produced by our sun, not under alien light sources, vapor lamps. Now imagine that aliens have abducted some humans for study, and they're studying our color vision. And they do all of their experiments under sodium vapor lamps. That's what they use. And they do that because they don't know, they kidnapped people, they came quickly, they kidnapped people, took them away. They don't know what changes in terrestrial illumination were like on Earth. They would never discover that we have a sophisticated computational system for maintaining color constancy on Earth. And they might even conclude that human color vision is irrational, poorly designed. They might speculate that humans did not need good color vision during their evolution. That's obvious, right? Yet the best known studies of judgment under uncertainty, probability inferences, use stimuli that are the conceptual equivalent of sodium vapor lights, and concluded that the human mind lacks mechanisms for reasoning soundly about probability. So case number 1 is going to be Bayesian inference. I'm going to show you how to elicit errors and make people look really, really irrational, as we were saying. And I'll show you how to elicit correct answers, all from the same statistically naive people. So in behavioral ecology, behavioral ecologists develop models of what we count as optimal foraging for various species. They did task analyses of adaptive problems related to foraging, because efficient foraging requires animals to make judgments under uncertainty. And optimal foraging models incorporate elements of probability theory into them. And a typical finding would be that insects, birds, and other animals behave like good Bayesians when they're making foraging decisions. Yet a still dominant view in psychology is that the human mind is too limited in capacity to do what bird brains and insect minds do. So again, I'm picking on Kahneman and Tversky. As they put it, in making predictions and judgments under uncertainty, people do not appear to follow the calculus of chance or the statistical theory of prediction. Instead, they rely on a limited number of heuristics, which sometimes yield reasonable judgments and sometimes lead to severe and systematic errors. So based on experiments, they made this conclusion based on experiments demonstrating conjunction fallacy, so thinking that A and B is more common than A alone, the neglect of base rates, answers that deviate wildly from the calculus of Bayes' rule. So why the difference? Why are the insects and birds doing better than us? Well, the non-human animals were tested using foraging situations, using ecologically valid situations as stimuli. The food were stimuli, they discover the frequencies on different patches. Humans were not. The stimuli were presented in a format that arose recently from large-scale data collection and with random sampling. Probability data was provided and requested in a format, as I'll show you, that did not exist ancestrally, with normalized frequencies, percents, randomly sampled, applied to a single event. Not what I'm going to refer to, and I'll tell you in a minute, are natural frequencies, which elicit dramatically different performance. So studying under, there's a medical diagnosis problem. What I'm going to show you should frighten all of you, because this is doctors at Harvard Medical School. This is the percent of them getting a medical diagnosis problem correct. So here's a sodium vapor lamp version of the problem. This is a real problem. This was published, it was first done on the Harvard medical students, at faculty and fourth-year clinical students. If a test to detect a disease whose prevalence is 1 in 1,000 has a false positive rate of 5%, what's the chance that a person found to have a positive result actually has the disease, assuming nothing about the person's symptoms or signs? The answer is actually around 2%, but most people say 95%. Be very afraid when you go to the doctor. This is the 18%, only 18% of the MDs at Harvard Medical School were getting it right. All of these are Stanford undergraduates. They do just as badly as the MDs when you give them the problem in the same format. If you merely clarify what false positive means, they do a little bit better. But this is the performance of the exact same people when you give them the problem in an ecologically valid format of natural frequencies. And I'll illustrate that in a different way. So how do you elicit poor performance? Imagine you want some ripe red apples from an orchard. There's a 20% chance that a tree in this orchard is an apple tree. If it is, there's a 75% chance that its apples are now red. But some of the other trees also have red fruit. 37.5% of them do. You can see a tree with red fruit in the distance. What is the chance that this tree, the one you're seeing in the distance with red fruit, is an apple tree? Okay, so what's the information here? This is the prior probability, the base rate of apple trees in the orchard. This is the true positive rate. H is for hypothesis, D is for data. So this is the probability of apple tree given that you're seeing red fruit. This is the false positive rate, the probability that something that's not an apple tree has red fruit. This is the posterior probability, the thing that we're looking for. And notice it's asking about this tree, a probability of a single event. So when problems are presented in this format, very few people answer correctly. Base rate neglect is common. That is, the answers don't seem to reflect the low prior probability of apple trees in the orchard, that there's only 20% of them are apple trees. And the normalized frequencies, the percents, are problematic because each of them is derived from a random sample of different subsets of the population of trees, making it difficult to recombine all the parts. So here's a representation of this problem. There's a tree in the orchard. The base rate of apple trees is 20%. And then here's what you're experiencing in the world. There's, of the apple trees, 75% of them have red fruit, etc. So there's a conditionalization event that kind of hides this base rate information from what's at the bottom. Each of these is normalized on a different population. So no information about base rates exists at this lower level. So the base rate normalized on the whole population. Here's the 20 trees in the orchard. This is the proportion that are apple trees. You know, you've got one with red fruit, green fruit, red fruit, red fruit. The true positive rate is only normalized on apple trees, on these. The false positive rate is normalized on trees other than apple trees. So you're seeing there are some cherry trees that have red fruit. And then what's the chance of a single event? It's a puzzling concept. A 20% chance that a tree is an apple tree. What's a 40% chance of rain today? Have you ever what do I do? Do I take my umbrella? What do I do? It's gonna rain or it's gonna not rain. Single events happen or they don't happen. The probability of a single event not be observed, and usually when people use them, they are expressing a frequency. They're trying to express a frequency, not always. It can reflect the subjective degree of confidence that will be true, but then you want to say based on what? And it's hard to combine these working parts that I was showing you because you need to use formulas, decimals, multiplication, division, etc. So with the problem put in this way, you need the formula to combine them, and this is Bayes' rule. It's nasty. You know, you're having to put everything in decimals and combine it just the right way. I would sometimes have subjects given the problem in this way, and they write Bayes' rule, exclamation point, and then they get it wrong. Way wrong, not So how to elicit good performance? Let's first consider the adaptive problem. The task analysis. Did our hunter-gatherer ancestors need to make judgments under uncertainty and update them as conditions change? Yes, that's necessary for foraging and many other decisions. Updating is needed because the success rate on different patches that you could forage on, it changes over time with how many others are exploiting that patch, what's the season, and so forth. So one hypothesis you might have is we might expect the evolution of mechanisms that were good at acquiring probability information and updating it under ancestral conditions. Was ancestral data about this available? Yes. In what form? The absolute frequency of objects and events. So you might think the encoding mechanisms for picking up and encoding this information might use representations with a compatible format. Representations of absolute frequencies are actually easy to update. I saw 4 apple trees in the orchard. Oh, here's another one, 5, etc. And so another hypothesis you might have is expect mechanisms that are designed to acquire those frequencies. And indeed, there was a large literature actually on what's called automatic frequency encoding. You're picking up the frequencies of events in the world automatically, incidentally, without trying to all the time. And many animals acquire frequencies, especially like number over time. That's central to operant conditioning. What about the sampling method? How was frequency data sampled ancestrally? Well, it's a natural sampling scheme. That is, your mind would be recording events as you encounter them in the world. And that's rarely a random sample from a population. Random sampling is needed for a normalized frequency for a percent to mean anything. And that's a product of modern data gathering techniques, not available ancestrally. So another hypothesis you might have is the design of procedures that operate on frequency representations should assume a natural sampling method. So natural frequencies were available. By this I mean the absolute frequencies of events as you encounter them. That is, naturally sampled, not randomly sampled. So in the example I gave you, the natural sample would be, what do I encounter while I'm walking through that orchard? So I'm walking through, my mind's automatically picking up which are apple trees, which trees have red fruit. It's just being, I told you. See, it's not working now. Computational devices malfunction in my presence. It's just a thing. This is, your mind's just picking all this stuff up. So a natural frequency representation of that same problem would be like this. Imagine you want some ripe red apples from an orchard. That orchard has 20 fruit trees. 4 are apple trees and 3 of them have red fruit. There are 6 other trees with red fruit. Really is not working. How many apple trees? I'm gonna pick this up. If I pick this up, will it still work? Just so I can be. Okay. How many apple trees with red? How many trees with red fruit are apple trees? This is a frequency version of the same problem. So, well, how many apple trees have red fruit? 3. How many trees are there with red fruit? The 3 apple trees and the 6 other trees that have red fruit. That's 9 trees. So 1 in 3. 3 out of 9, 1 in 3, 33%. Really easy. Here's what's happened. There's a representation of that problem. The idea is that the natural frequencies of encounter is just being at this lower level, is being recorded by your mind, which includes the hits which are apples that are red, apple trees with red fruit, and the false alarms, other trees with red fruit. It's just hits plus false alarms. So with this ancestral format and sampling method, normalized frequencies are unnecessary. The low base rate, the mechanism wouldn't necessarily be designed to take a base rate of telling them it's 20% of apple trees, because the low base rate's accounted for in your encounter rate. When apple trees are rare, you encounter fewer apple trees. In this case, it was 4 out of 20. So is the false positive rate. It's implicit in what you picked up. All the working parts are in the same format. It's easy to recombine them to answer new questions. And with natural frequencies, 9-year-old children do better than faculty at Harvard Medical School. So you can give them icon arrays that represent natural frequencies. And you can say, okay, out of every 15 cookies in a cookie jar, 3 are round and made of chocolate. The other 12 cookies are square. Of the 12 square cookies, 5 are also made of chocolate. Imagine a pile of chocolate cookies from the jar. How many of these are round? Well, we're seeing, for example, here, we're seeing 8 chocolate cookies and 3 are round, 3 out of 8. The 9-year-olds know it too. And they give the correct, spot on correct, not generally correct, posterior probability 64% of the time, and 78% of them got 50 to 100% of the problems right. Okay, case study 2. Judgments that look like normative violations may be very well designed for solving a recurrent adaptive problem, but one that scientist is not looking at or considering. The example I'm going to give you for this is risky decision-making versus prospect theory. So the claim has been made by Tversky and Kahneman that losses loom larger than gains, by which the empirical claim is that in choosing between a risky option and a sure option with the same expected value, people are willing to take a bigger risk to avoid a loss than to achieve an equal sized gain. The normative theories challenged by the research I'll describe to you was expected utility theory predicts indifference between options that have exactly the same expected value. But I'll show you that people are not indifferent. And rational choice theory, the underlying preferences should be transitive, but what I'm going to show you is that loss and gain frames elicit so-called irrational preference reversal. So here's the most famous of these problems from Tversky and Kahneman. Imagine there's an outbreak of a disease that it was called the Asian disease problem, but it would be politically incorrect now for me to call it that. Imagine that there's an outbreak of a disease that will kill 600 people if nothing is done. Which of 2 programs to combat the disease would you favor? If program A is adopted, 400 people will die. If program B is adopted, there's a 1/3 probability that nobody will die, and a 2/3 probability that 600 people will die. The expected value is 200 lives saved, 400 lives lost. In program A, it's with certainty. With program B, it's on average, but the expected value is the same in both cases. Here's the gain frame. If program A is adopted, 200 people will be saved. If program B is adopted, there's a 1/3 probability that 600 people will be saved and a 2/3 probability that no people will be saved. Again, the expected value is identical and the same as in the loss frame. 200 lives saved, 400 lives lost. So notice that the loss and gain frames, they express situations that are logically and mathematically identical. They have identical consequences, the same material consequences. 200 live and 400 die. So with normative theories of rationality, expected utility theory, they have the same expected value, so you should be indifferent between A and B. But people are not indifferent between A and B. When you give them the loss frame, 80% of them prefer B, not 50%. Rational choice theory as applied in economics would predict that making this, that whatever your choice is, whichever you like, the program A, program B, that whatever you choose in, that if you choose A in the loss frame, you'll also choose A in the gain frame. Because the options are defined by their material consequences. And the loss and gain frames have exactly the same material consequences, 200 and 400 die. So you should always choose the option with the highest utility given your preference order. This preference order is stable, perhaps described by a utility function, a ranking of all conceivable options. And rational choices will be choices that reflect an underlying preference order that's transitive, so that if you prefer A to B in one choice set, you should prefer it in other choice sets. So you won't prefer B over A in another choice set. So preference reversals would be irrational. What happens? In the loss frame, 80% prefer the risky option, but in the gain frame, 70% prefer the sure option. It's a preference reversal. Because the material consequences are the same for loss and gain frames. So it looks like people are doubly irrational. They are violating expected utility theory and they're violating rational choice theories. And that was the claim being made. The explanation that they proposed was prospect theory. They proposed that loss aversion to losing things, is a stable preference. And so you should be willing to take a greater risk to avoid a loss than to achieve an equal size gain. And the loss frame activates loss aversion was the idea. And supposedly, no normative theory of rationality can explain these choices. Now, in the meantime, and I mean literally in the meantime, I was present in a lab group of Amos Tversky's where he's saying there's no normative theory that can explain what we're seeing. But there was a normative theory from behavioral ecology that explains these kinds of results without invoking framing effects and correctly predicts when choices will flip from high to low variance options. It's a branch of behavioral ecology called optimal foraging theory, and more specifically risk sensitivity theory. And the key concept is what is your need? What is your need level? So imagine you're a bird. This is what it was designed for, birds. And you have to decide which patch to forage on, A or B. And let's say each patch has, the expected value is 200 seeds a day, whether you forage on one or the other. Patch A is a low variance patch. You will, with certainty, get 200 seeds that day if you forage there. And patch B is a high variance patch. There's a 1/3 chance that you'll get 600 seeds. There's a 2/3 chance you'll get nothing. Same expected value. The question is, how many seeds does this bird need to live to tomorrow? If its need level, if it only needs 200 seeds to live to tomorrow, then clearly it should forage on the low variance patch. It's certain to get it. It might die if it goes to the high variance patch. But what if its need level is 400 seeds to live to tomorrow? In that case, it really should avoid patch A because it's not going to get 400 seeds. It might get 400 seeds on the high variance patch. So that's what the rational thing to do would be if your need level is 400. So applying this to that disease problem, the question is, for each subject, how many lives does a subject feel that they need to save, that it's really important that they save X number of lives? This is work by Sandeep Mishra and Larry Fittick. So what they did was they either specified a need level, like you need to save a minimum of 200 lives, or you need to save at least 500 lives, or they elicited one. So either the experimenter specified it or the subject specifies in advance. You say, how many lives do you feel you need? The person says, one person says, I feel I need to save all of them, or 300 of them, etc. Or they have the subject report after choosing. And they also tested certainty versus low variance as well. Oh, will it work now? Ah, yay. Okay, thank you. You didn't believe me. Okay, thank you very much.
Stronger, he said.
What they found was that people choose rationally given what they think they need to do. If they felt they needed to save 200 lives, they picked the sure option. If they felt they needed to save 400 lives or more than 200 lives, they picked the risky option. And there were no framing effects. It didn't matter if you put it in terms of loss and gains, not at all. So when you specify no need level at all, then the framing effects reappear. Why? They found that it's because whether you put in a loss or gain frame, it changes the number of lives that a person feels that they need to save. In a gain frame, it's a kind of cover your ass kind of situation, like I need to save 200 lives. I'll be in trouble if I don't do that. In a loss frame, people, when you ask them afterwards, they said, I need to save more lives. So they're reporting their minimum after making a choice, and their choices were exactly matching what they thought they needed to do. It also explains ambiguity aversion, the same model. A lot of economists keep saying people have a preference, an aversion to ambiguity. The claim was that people avoid ambiguity because they have a preference for known risks over ambiguous distributions of risk. A risk sensitivity analysis, you might think, well, an ambiguous option is usually going to be interpreted as a high variance option. I don't know what's going to happen. It's a distribution of possibilities. So you can do tests where you dissociate variance and ambiguity. You can say, here's two boxes. There's 100 balls in each box, black and white balls. One box is a known risk box. You say 30 of the balls are black and 70 are white, and then you change it in different conditions to half, 60%, etc. Then the ambiguous box, you say there's a probability of 0.5, a half on average. And then we're going to determine it by drawing from poker chips what it is. And then you vary the need level. How many black balls do you need to draw in order to win, to progress to the next stage where you can win something? What happens? The ambiguous box that supposedly people have an aversion to, it's preferred when it's more likely to meet their need level. This is subjects choosing the ambiguous box, a percent of them. Black is how often they're doing it when their need level is higher than the expected value. White when it's lower. This is when the known risk box is 30%, 50%, etc. So you're seeing people choose the ambiguous option when that would be more likely to satisfy the need level. And their actual probability of winning tracks pretty nicely their decisions. So risk sensitivity theory, this is a normative theory from behavioral ecology. It shows that need level determines when risky versus sure options are chosen, regardless of loss versus gain frames. It eliminates framing effects. There are no framing effects. It predicts when people will avoid versus prefer ambiguous options over known risks without positing odd preferences, such as loss aversion or ambiguity aversion. And it shows that choices that look like preference reversals are not preference reversals, they're rational choices. Case study 3, this will be the last one. Choices that deviate from economic rationality may be the most adaptive fitness promoting strategy, not a bias. An example I'm going to use is evolution of generosity in one-shot interactions. So games theory is a very interesting source of normative theories about social behavior. It's a tool for analyzing strategic social behavior, how agents will behave when they're interacting with others who can anticipate and respond to their behavior. Economists use it to analyze how people respond to incentives that are present in the immediate situation. The models typically assume rational actors who calculate the payoffs of alternative options, anticipating that other players will do likewise, and choose the option that's most likely, that this is the standard assumption when this started, that's most likely to maximize their short-term profits. That is, they assumed homo economicus preferences. Evolutionary game theory, it's a different source of normative theories. It's related but different. It does not assume economically rational agents who can reason about the reasoning of other agents. It's used to model interactions amongst agents endowed with well-defined decision rules that produce situationally contingent behavior, called strategies. Although there's no conscious deliberation that's implied by the use of the word strategy or ruled out. So it's been applied to cooperation in bacteria or fighting in spiders. The results are either derived analytically, or in more complex cases, you do an agent-based simulation of natural selection. So whether the decision rules being analyzed are designed to regulate foraging or fighting or cooperating, the immediate payoffs of those decisions in food or resources are translated into the currency of offspring produced by the decision-making agent. And those offspring inherit their parents' decision rule. And a decision rule or strategy that garners higher payoffs leaves more copies of itself in the next generation than alternatives that garner lower payoffs. So by analyzing the reproductive consequences of alternative decision rules over generations, evolutionary biologists can determine which strategies natural selection is likely to favor and which are likely to be just selected out. And that source of normative theories can be tapped for any domain in which organisms make consequential choices. So it's been famously applied to the evolution of cooperation. Extensively modeled with evolutionary game theory, in particular repeated prisoners' dilemmas, with clear results. Strategies that indiscriminately provide benefits to others, that is, including those who do not reciprocate, are eventually eliminated from the population because they incur reproductive costs without compensating benefits. They're outcompeted by strategies that cheat, that accept benefits without reciprocating them. And this is a failure. These strategies that cheat, it's a failure to reciprocate by design, not by accident. By design, I mean either intentionally or by virtue of the calibration of the mechanism. Now I'm going to define a cheater as an agent who's endowed with decision rules that accept benefits offered by other agents without reciprocating or otherwise satisfying whatever their requirements are. Now, accidents and innocent mistakes don't reveal a cheater, because even really good cooperators are going to sometimes fail to reciprocate due to injury, foraging failure. They just didn't find any food, they forgot, it's an oversight. There would be a fitness error to exclude good cooperators for that reason, because we're going to miss out on strings of benefit-benefit transactions. Those selection pressures have shaped our psychology in various ways. I don't have time for this other case study. I've done a lot of work in the past on cognitive adaptations for reasoning, because a cognitive adaptation can be specialized for a specific domain. And I've done a lot of research on that, and therefore equipped with representations and procedures that are content rich rather than content poor, what philosophers might have called innate ideas a long time ago. And there's inference and implicit categorization procedures, activated cooperation, that are quite content rich and that distinguish between intentional failures to cooperate and innocent mistakes. It's reflected in our psychology in dyadic cooperation, social exchange situations. It activates inferences and information search procedures that cause a detective violations of agreements to exchange when those could reveal cheaters, but not when they would result from an innocent mistake. In collective action group cooperation situations, there's an implicit categorization measure. You don't even know that it's going on. It's something your mind is doing out of conscious awareness. And it shows that not all failures to contribute are the same. That intentional, when somebody fails to contribute to the group collective action by intention, that person gets tagged by your mind as a free rider and you have the negative opinion of that person. But when you don't contribute to the same extent, accidentally or by foraging failure, they're still tagged as a good cooperator. So repeated interactions select for reciprocation, and the reason that natural selection favors strategies that deliver benefits to others contingent on reciprocation is that they outcompete defectors, that is, strategies that do not deliver benefits. Because because reciprocators harvest the fruits of mutual cooperation over many repeated interactions, that's why it gets selected for. So how do we then explain generosity in one-shot interactions? The benefits given to someone that you're never going to meet again. So no reciprocation is possible. So this was initially a puzzle in behavioral economics. Behavioral economists study cooperation in a laboratory by having people interact in various games with monetary payoffs for different choices carefully controlled. Dictator games, prisoner dilemma, you all know this. And what people found was, in one shot, anonymous, I tell you, you're going to interact once and only once with somebody. You're never going to see them. You're never going to know who they are. They're never going to know who you are. It's completely anonymous. A homo economicus set of preferences would predict no generosity, no cooperation, no trust, no punishment. Yet in one-shot anonymous games, people give more, cooperate more, trust more, and punish defections more than the homo economicus preferences would predict, even when the experimenter tells them that the interaction is one-shot and anonymous. But why? Generosity in anonymous one-shot games is irrational given the standard theories, including some evolutionary ones. So what explains, this was called excess altruism. So what explains the excess altruism? Because delivering benefits in one-shot anonymous interactions was considered irrational, some social scientists viewed it as evidence that the psychology of cooperation was shaped by group selection rather than selection operating on individuals. The question is, are these behaviors really excess altruism that is beyond what can be explained by selection on individuals for direct reciprocity? So shift your focus a little bit to what I'm going to call adaptationist game theory, where we model the information processing problem and then let the psychology evolve in response. Selection never occurs in a vacuum. The physical and social ecology of a species shapes the design of its adaptations, and our hunter-gatherer ancestors lived in small, interdependent bands, which had many encounters with individuals from neighboring bands. Adaptations for direct reciprocity evolved to regulate cooperation in an ancestral world in which most interactions were repeated. So there would have been a high prior probability that any given action will be repeated. And that should be reflected in the design of the computational adaptations that regulate direct reciprocity. So should the fact that you've interacted, and also the fact that you've interacted at least once with a person is also a relevant piece of data, because in agent-based models of a hunter-gatherer kind of social ecology, meeting an individual once turns out to be a good cue that you're gonna probably run into them again. So what Andy Delton and Max Krasnow and John Tooby and I did, they did the hard work, was we modeled the information processing problem and then let the psychology evolve in response. Because whether an interaction is one shot or repeated is a judgment made under uncertainty. And we asked, what decision rules does selection favor when this judgment under uncertainty problem is modeled? Well, in most agent-based simulations of the evolution of cooperation, the behavioral strategies are particulate. They don't change over time. They become more frequent and less frequent in the population, but the strategy remains the same. They don't have internal cognitive components that can evolve. In the simulation environment, in most of the studies, it either had one-shot or repeated interactions, not both. But what happens if these strategies have a cognitive architecture that can evolve, and the social environment includes both one-shot and repeated interactions, as it does in real life? It turns out that generosity in one-shot interactions evolves incredibly easily when natural selection shapes decision rules for regulating two-person reciprocity under conditions of uncertainty. So we did it in different ways. In real life, you never know with certainty that you'll interact with a person once and only once. Well, you know the second before you die. It's like, oh, I'll never see that person. Categorizing interaction as one shot or repeated, it's always a judgment made under uncertainty based on probabilistic cues. You know, am I far away from home? Did this guy marry into my band, etc. So in deciding whether to initiate a cooperative relationship, a contingent cooperator is going to use these cues to decide whether to cooperate or defect. So Using these probabilistic cues, you have to make trade-offs between two different kinds of errors. A false positive, where a one-shot interaction is mistakenly categorized as a repeated interaction. So you cooperate, but the one-shot partner defects. In that case, you suffer a one-time loss. Or a miss, a repeated interaction disguise, it's gonna be a repeated interaction in the future, but I've mistakenly categorized it as a one-shot interaction. So you defect, triggering a defection for what could have been a long-term cooperative partner. The cost is a missed opportunity to harvest gains in trade from a very long string of mutually beneficial interactions. So what happens when you let adaptations evolve? In the population of contingent cooperators, like tit-for-tatters, the cost of the miss is usually much higher than the cost of a false positive. And so in these agent-based models of contingent cooperators, decisions to cooperate or defect were based on two pieces of information. The base rate of one-shot interactions in the population, which varied up to 70%, which is very high. And a Q summary for each partner. So Denise would have a number on her head. She'd be an agent in the simulation, but she'd have a number on her head that is probabilistically associated with being either a one-shot partner or a repeated partner. And then we saw how the cognitive architecture uses that information and let it evolve. So this Q summary, it's a hint, as I said, about whether it's one-shot or repeated. And the Q summaries are never perfect predictors. They're drawn from two normal distributions. This is a distribution of numbers, Q summaries for agents who are going to have repeated interactions, and this for one-shot interactions, and they overlap by different amounts in different runs of the simulation. And they're used to compute a belief that the interaction will be one-shot or repeated. And agents cooperate when they believe an interaction is repeated, otherwise they defect. So what can evolve in each simulation? In the first set, motivations to cooperate or defect depend on the belief. These don't evolve. If you believe it's one shot, you defect. If you believe it's repeated, you cooperate. What evolves is a decision threshold determining how strong the cues that the interaction is one shot need to be before the agent defects. And what happens is that selection favored a really, really high threshold of evidence that this is a one-shot cooperator. So such that most interactions were classified as repeated, triggering cooperation. This is based just on the Q summary. What's the decision? How high does Denise's Q summary have to be before I say she's a one-shot interaction? And the credulous agents evolved because of the cost of missed opportunities was greater than the cost of cooperating in one-shot interactions. What's more interesting is the second simulation. In this one, the motivation to cooperate evolves, and that's a regulatory variable that determines the probability that an agent will cooperate given its rational belief that the interaction is one shot. These little agents are perfect Bayesians. They are equipped with Bayes rule. They are given innate knowledge of the base rate of one-shot interactions in the population. So they have a correct prior probability, and they form rational beliefs about whether an interaction is one-shot by using Bayes' rule to integrate cues that the given interaction is one-shot with perfect knowledge of that base rate of one-shot interactions in the population. What happened is, and what's evolving is the probability that you cooperate given your rational belief that this is repeated or this is one-shot, etc. Selection favored designs with a very high probability, 70 to 90% of cooperating, given the rational belief that the interaction was one shot, with very modest gains in trade and not even that many encounters for the repeated interactions. And that was true even when the base rate of one-shot interactions was unrealistically high, 50 to 70%, ridiculously high. So this willingness to cooperate given a rational belief that the interaction is one shot is actually apt, because when you talk to Tversky, Kahneman, when we talk to people, they say, well, these subjects who are doing this excess altruism, when I told them that it's one shot and it's anonymous, and when I asked them afterwards, did you believe me that it's one shot and anonymous, they said yes. But if you think about it, that's a cue from the experimenter. The experimenter tells you, you have a lifetime. You walk into the lab with a lifetime of experience of one-shot and repeated interactions. What the experimenter tells you is one cue, that the interaction would be one shot. There was no group selection needed to select for generosity and interactions you believe rationally are one shot. And that disposition to cooperate in one-shot interactions, it's not a mistake. It's not an irrational bias. It evolved. It's the most adaptive, fitness-promoting decision. So by applying this adaptationist program, it can reveal sophisticated computational systems that no one looked for before and nobody imagined existed. It also, I would argue, it provides a meta-normative theory of rationality that's actually useful and appropriate for studying the cognitive architecture of organisms that evolved by natural selection. It'll let you find really interesting things that nobody thought to look for. That's it. Thank you.
You have questions?
You can make them look rational.
Carlos.
I really like your explanation for choosing program A or program B on the idea of how many people do you think you need to save. But what if, from a public policy perspective, actually you want the expected life to be saved to be the criteria that we should use? What do you do on those occasions? How rigid is this adoption that we develop under like ancestral conditions?
A public policy perspective is one of these modern problems of a mass society.
Yeah.
And that's going to be like it's either going to be a decision of technocrats.
Yes.
How many people do we feel we must save? What percentage of the population must we save? Or there can be public discussion about it to come up with, well, how many deaths are we willing to, this happened during COVID, right?
Mm-hmm.
How many deaths are we willing to tolerate? That's what's gonna, for public policy purposes, that's the kind of conversation or process that's gonna set a need threshold. And then which policy you choose is gonna depend on that. You're gonna have some policies that won't achieve that and other policies that may achieve that. And, what I'm talking about here is how does an individual make
That's
those
why
decisions?
I like the explanation to understand the choice of doctors that are implementing alternative programs, for example.
There's Gerke Grenzer, who was talking about this for a long time. He actually has, for continuing education for doctors in Germany, a 1 weekend course. And 1 weekend, he just shows them the natural frequencies, how to do it with natural frequencies. They obviously, graduates can do this, 9-year-olds can do this. They learn to do it and they don't make the mistakes anymore. It also has implications for if you're a doctor, how you present risk to your patients. Because if you show them an icon array, and these are really interesting when it's like for prostate cancer, because there's arguments about should you screen everybody for prostate cancer or should you not? Because there's lots of false positives screened for prostate cancer. There's been some studies where one group of men wasn't screened and the other group of men was screened. And then they looked at how many died of prostate cancer and how many had impotence, incontinence. I mean, there's lots of bad consequences of the surgery, right? And you could see in one flash, when you look at these icon arrays, there was no difference in the number of men who died of prostate cancer. But the ones who were not screened didn't have all these bad, the ones who were screened, many of them ended up incontinent and impotent and so forth, but there wasn't a difference in the deaths. So these icon arrays are really powerful because you don't have to be numerate. In fact, one of the studies that he did with the kids was kids with acalculia. And for those kids, he just asked them, well, which is more likely, that it's going to be for like the cookies, but given as a chocolate cookie that it's round or, square. The kids with acalculia were getting the directional prediction right. And they have so is it informed consent when you're not giving people, if you give people information in a format that they don't understand, is that informed consent? I noticed that when I need to decide on treatments, they would give me information about how good the treatment is as a relative risk. Like this will cut X-rays will cut your probability of recurrence of breast cancer in half, you know. But then when you ask, well, what are the possible side effects? They give it to you as an absolute frequency. Oh, don't worry, it's only like 1 in 10,000 or 1 in 1,000 people who do it. No, you have to give them both. You can say, the Women's Health Initiative, I'm sorry, this is a bugaboo of mine. The Women's Health Initiative study, the women who were 50 to 60 when they started this, and they put on, it was a random sample, gold standard, double-blind study of the effects of hormone replacement versus no hormone replacement. They stopped that study after a certain amount of time because for the women who were also on progesterone, there was an increase, a 24% increase in incidence of breast cancer. Oh no, so they stopped the study. That 24% increase is an extra 2 to 4 women in 1,000. The question is, do you care? And it turns out that the all-cause mortality is lower in the women on hormone therapy than the women without hormone therapy or on placebo. You need to know these absolute frequencies because you need to, do I care? I don't care about odds like that. So I think it has a lot of.
But you said about informed consent, we need, I really like this idea that you need, the really informed consent is the one that we are prepared for. You
Yes.
can't have informed consent like
Yes.
given by aliens.
Yes, yes, thank you, exactly that. You don't want alien language for the informed consent. People's eyes sort of just like glaze over. I was very entertained this past winter because one of my colleagues who had to make decisions about not a dangerous form of breast cancer, but a form of breast cancer. She's the person who teaches stats in our department, and she's a whiz. And she goes to all the literature and she's reading everything, and she goes to talk to the radiation oncologist, and he says blah, blah, blah. And she says, but this study shows this, and that study shows that. And it drove him crazier than I had driven the same man.
Poor guy.
Yes.
From this perspective, under a logically valid environment or framing of the problem, could you say that the axioms of rational economic choice may stand, may hold?
Yes.
So
Not only can you, but Ricardo and Betsy Barbado and Daniel Caesar and I did this with moral trade-offs. And because your preferences don't have to be homo economicus preferences. There's nothing in rational choice theory that says that has to be your preferences. But when Vernon Smith started and his colleagues started to do these experiments in the lab, one of the things he wanted to test is, do people in the lab, when they're in small group cooperations, do they act with homo economicus preferences? And very quickly it became clear that the answer was no. So, and there's different ways of thinking about it. The way I think about it and the way that actually he wrote about it is that you're having, your mind's designed for small scale interactions. So when he brings 27 people into the lab and he has them interact in these small groups, the programs that are being activated by default are the ones that evolve for these repeated cooperative interactions where we know each other and so forth. Homo economicus preferences work great if you're talking about durable goods in the market. The ones where their value in use is, you're not trading them later, and everything works terribly for asset markets. But no, you don't have to have homo economicus preferences. And what we found when we gave people a moral dilemma, if this was an incredibly long talk that was like 3 hours or more, I would have talked about that research. What we found was that we gave people a moral trade-off that was like, there's a war and there's different ways of stopping it. You can bomb this many civilians, or you can have soldiers only fight, or you could do a combination of these two things. And we weren't specifying that you have to have this preference or that preference or anything like that. But we asked the question, we did this using revealed preference methods. And we gave them different scenarios where sacrificing one civilian might save 2 soldiers, 4 soldiers, 7 soldiers, et cetera. We varied the cost effectiveness of killing civilians, and how many total civilians and soldiers are saved. And people's choices, they made 21 of these choices, and they respected GARP to an insane extent. They were respecting the generalized axiom of revealed preferences. This has nothing to do with Homo economicus. And different subjects had weighted these things differently, but their choices were internally consistent. They didn't have preference reversals. The majority of subjects had 0 GARP violations, and 90% of them had fewer than 7, which is really, they did better than if you took people with 0 violations. Ricardo did this, and he created agents out of the people who had 0 GARP violations, so that are making perfectly rational responses, no violations. And then Ricardo introduced 1 random error per agent to mimic like 1 hand tremble. My hand trembles once, like my hand kept trembling with this thing today. And subjects were doing, we call these the rational +1 tremble agents. Subjects did better than they did. They did better than a completely 0 violation guy whose hand trembled once out of 21 times. So that's a case where absolutely people were, they were respecting axioms of rational choice. Their choices were consistent with those axioms. No preference reversals. This is so not like what Tversky and Kahneman said. You know, we had a bet years ago about this, and Ricardo said, if he was getting annoyed with these dual process theories, and he said, if we do this with GARP, people are going to be rational, you know. And I said, what? You know, this is like 20 years or more of research from Tversky and Kahneman telling us that people make preference reversals all the time. And he said, well, let's see. And this is a bet he won. Completely.
Lida, we want to invite you for a cocktail so we can keep talking outside, because I know you have a lot of questions from them. But let's have something to drink and to eat, okay? Thank you very much.
My pleasure.